So my name is Matan Breizman, and I'm leading the Crimson project. Today with me is also Aishwarya, who will be also presenting our work in progress in the Crimson project. So a few folks joining in, but I think we can start. So as we know, today we'll be presenting Crimson for Tentacle release. What is there, what to expect. I'll start with a brief, thanks, Aishwarya. I'll start with a brief background for those of you who are not familiar of the hows and whys of the Crimson project. And later on, Aishwarya will be giving a brief overview of PG splitting in Crimson. Then we'll go to some performance numbers, what's currently there, and finally, we'll finish with SeaStore. So let's begin. We all are aware in this room that hardware today is quite different than what we had when ceph was initially introduced. We know that ceph has been here for almost 20 years. We've seen that earlier today and this morning. And from that time till today, storage devices and networking devices keeps improving. Their I/O speed keeps improving. And we cannot really compare the speed of hard disks that ceph was originally implemented to work with to NVMe's we have today, which could draw around more than a million IOPS. Another distinct change we have is in the number of, in the CPU architecture. We can see here in the slide, a famous slide from anyone who is looking into CPU train data or anyone who has been to a Crimson talk. We can see in the black trend in the lower part that up to around 10, 15 years ago, we only had single-core CPUs. And from that time till today, the number of cores kept doubling up to almost more than 200, I think, we have in some modern CPUs we have today. But the third point here, and it's the point that we're trying to solve here, is that the single-thread performance remains roughly the same. And that means that for us to really make use of this new and faster CPUs and architecture that we have, and most specifically the number of cores, we really need to make sure that the performance depends on the coordination across multiple cores. Performance today no longer depend, like back in the day, on the single performance of one core, but the fact that we need to share data and to have synchronization across multiple cores that requires us to use expensive synchronization primitives, such as taking logs caused from the multi-threading model. So that may actually cause our application to not be able to scale up to the number of cores we have. So for that, we have the shared nothing model. That's actually what it comes here to solve. The shared nothing model actually shards data structure and work into individual cores, and by that, we avoid the cross-core communication, and we're really able to not pollute our memory with this expensive context switches we have, as we've seen in the earlier PUPy slide. So before I go over Crimson and the goals and how, we need to remember that ceph today is highly scalable, and we all know it and love it for that, of course. But the fact and the way that it's been architecture may be quite heavy on CPU usage, and we have a lot of place to do actually better. So our goal here with Crimson is to minimize the CPU overhead per I/O. We'll do that by avoiding the context switches and reducing latencies. And for that, we'll be able to exploit these fast storage devices we have today, like NVMe's and ZNS, and so forth. So how we're planning to do that? Essentially, Crimson is a full rewrite of the classical, we name it classical, for the current OSD implementation we have today. We like to name it an efficient rewrite of the entire I/O path. We do that with the Seastar framework. This is the Seastar with Cedar. Seastar framework is a C++ asynchronous high-performant framework, which is offered by ScyllaDB. And we're using that to actually implement Crimson. So the main thing we need to remember here, the implementation is a single thread per core. We no longer have a multi-threaded model, no need for locks, no need for context switches. Yeah, so let's see how it actually looks. I'll start with a brief high-level abstract overview of write in the current architecture, and we'll see how Crimson handles the same write. So we have three main components. I think these are the three main components when we're talking about handling a write in the OSD layer. So the first one is the messenger. It's responsible to send messages between daemons, as it says. Basically, it's the communication layer in Ceph. It's responsible to send messages between daemon, clients, anything that we all know, OSDs, monitor, and so forth. Second, we can see that there is the PG, and PG is an in-memory state, which is responsible for operation ordering, I/O replication, failure recovery, and all the magic that actually Ceph knows how to do. This is where we do it. Lastly, the object store, the transactional interface. This is today we have Blue Store. Back in the day we had File Store. And in the end of the presentation, I'll be briefly going over SeaStore and explain why we need to also have a new backend for Crimson project. So for the classical OSD I/O pipeline, it looks something like this. We pick up the message off the wire using a messenger thread. Later on, the PG handles using a worker thread, collects the message, handles it, and when the transaction is ready, passes it to the queue for the object store to pick up. The object store, Blue Store in this case, will pick it up along with anything else in the queue, commit it to the store, and send a reply message back, again, using a worker thread. What we need to understand here is that each thread transfer we have from each thread pool we see here requires an inter-thread coordination over the context of the queue. And with PG state in particular, more than one thread may need to access the internal data of the PG, and that may cause lock contention, which will avoid, under certain workloads, will act as the performance bottleneck for the OSD. In Crimson, on the other hand, we can see that we have each core has one thread, and each core can handle by itself from start to beginning, from beginning to end, entirely the I/O path. We have the messenger, the PG, all in a single core, a single thread, and where classical uses operation system context switches and the operation system scheduling, in Crimson, we use a user space task switch. It's the scheduler that is offered by Seastar, and when a task is blocked, logically blocked or idle, it voluntarily yields control to another task on the same core. So let's see it in these two graphs that comes to explain the difference between context switch in the operation system to a task switch. So in the left side, we have the classical OSD. In the right side, we have Crimson. So the classical OSD, when it sends a request to a disk for an I/O read, let's say, we may have a context switch. We may let other thread to actually be executed or scheduled on this core. And later on, when we get the response back, again, we need to copy all the data back, and we continue with our work. For Crimson, on the other hand, when we send a request, we immediately get a future. We call it a future. For those of you who are familiar with asynchronous concept, is a result that may not be ready yet. And once we get this future, depending if it's ready or not, we do other work on the same core. No context switches. When the result is ready, we just switch back to this task. Now, with the task switch, we also need to copy some of the continuation data to actually return to this task, same as context switch, but we cannot really compare between the two operations, most notably the size of the block thread stack size, which is really takes much more memory and may really pollute our cache and our overall bandwidth. So we can have millions of task switches, and we cannot really compare it to a full-blown context switch in the operation system. So next, we have here Aishwarya, which will be given an example of how the differences is actually implemented with a real workload, such as PG splitting, which is being implemented currently by her. So go ahead, Aishwarya.
Thank you. Can you hear me? OK. Hey, everyone. I'm Aishwarya. And I started working on Crimson in the past year. And the feature I started with was PG splitting. So we thought it might be a good idea to compare what the design differences are when you're rewriting something in the Crimson OSD. So a brief intro to PG splitting for those who are not familiar with it. Currently, in the classical OSD, Ceph can split existing PGs into smaller PGs in order to increase the number of PGs for a pool. This feature allows a cluster to grow over time as its storage requirements increase. There are two ways to induce PG splitting. The first one is you can manually increase the PG num of your pool. And the second one is you can enable the PG autoscaler, and it'll make a call as to when you need more PGs in your pool. So a very high-level workflow of PG splitting would look something like this. When we receive new cluster state information or a new OSD map, we send it to each OSD. And each OSD will check if the PGs it has need to be split. So basically, it'll check if there has been an increase in PG num for a particular pool. And if there has, it'll check if it has any PGs that belong to these pools. Once it makes a calculation of how many new PGs need to be created, so for example, if there was a pool with 4 PGs and the PG num has been increased to 16, the existing PGs need to be split into 4. So once it returns a list of how many new PGs need to be created, we call these PGs children PGs. And once we have that, we initiate PG creation for each child PG. So now what happens currently in the classical OSD is that, like Matan mentioned, because we have worker thread pools, we need to acquire locks to perform this PG splitting operation. The first one is to acquire the PG lock, so that there's no other operation that can access the PG's data while we're splitting. And the second one is that in classical OSD, we make use of shared queues. So we also need to access the lock to that queue. And yeah, the other thing is, because of the way the code is written currently, the splitting check happens 1 PG at a time. So why does this not work in Crimson? With Crimson, we're trying to achieve a shared nothing architecture, like Matan has mentioned before. What this means is that what we ideally want is that once an operation starts on a PG, we want it to complete, and we don't want another thread to interrupt this. So I'll move on to what we want splitting in the Crimson OSD to look like. Sorry, I added some animations that no longer make sense. Okay. So when we receive a new OSD map, each OSD receives it. And in Crimson, in this example, I have an OSD that's running on 4 cores. And the OSD will send a copy of this OSD map to each of the cores. And each of the cores maintain their own copy of this map. And then they start checking if the PGs that are mapped to them need to be split. If they do, it's the same workflow that they will create a list of children PGs, and then we initiate PG creation for each of them. But what's the difference over here is that, one, as you can see, if it's 4 cores, what we get is that we initiate PG splitting for 4 PGs at a time. And the second thing is that everything for a particular PG is going to happen just on 1 core. So we're eliminating the need for locks. Going into more details as to how we do this is, of course, we rewrite the code to be executed asynchronously on each individual core. But in particular, we make use of a module in Seastar called the Seastar sharded template helper. What this does is that it manages a sharded service by making a copy of it on each logical core. So since there's a copy on each core, no other thread can access it, and we don't need to maintain any kind of locking system. It also provides us with mechanisms to communicate with each shard's copy, although we try to avoid doing this, but the option is there. And of course, in case you forgot, it's lock-free. I'm going to hand it back over to Matan to take a look at some of the numbers regarding these changes.
Thank you. I think my microphone is back on. Yeah, cool. So numbers. Let's see. This is from a workload of RBD on a replicated pool for a random read on 4K block size. And we recorded the number of context switches, CPU migration, page faults done in both the kernel and in the user space. So we can see that the gray trend here is of classical OSD. We see that we have almost 35,000 context switches per second done in our kernel and user space. And almost half of those, the 17, the gray trend there, is resulted in CPU migration. A CPU migration is when a thread wakes up on a different core than the one that was scheduled earlier, so we need to actually copy all the data. While in Crimson, we have almost no context switches. Basically, it comes to prove the architecture worked. No CPU migration, that's what we want to avoid. And also, as a nice to have, page faults, we almost have none in Crimson, while in classical OSD, we have around 74 per second. And a page fault is when the cache miss usually requires a disk access, so that may also cost us some performance results. I will note that you see in the red lines, this is Crimson. This is excluding the backend, excluding BlueStore. Currently, we run Crimson with BlueStore as a backend, and I'll explain soon why. And BlueStore is written, as we know, with the current architecture we have. So we just separated the OSD layer, but it comes to show the results. Another cool test, which was done by Inshin from the Intel team, we also have the messenger component that, same as PG splitting, also was rewritten to work asynchronously with Crimson. So we can see here the blue one, this is Crimson Messenger, and this is a ping-pong comparison. By ping-pong, we simply send pings over and wait for the reply and count the number of replies we're able to handle. This is without actually going into the backend or even to the OSD layer. This is simply the network layer. And this is, I think, the best example to show the ability to scale over a number of cores. The more cores we had, we really able to scale much higher, as expected. We can see that we're in classic messenger, around 8 or 16 cores. We start to have diminishing returns based off the number, the context switches that we have to do, and the number of cores does not really benefit us more. Crimson is really able to scale more and more. Yeah, and for actual I/O results, before going into the numbers here, I will note that performance is a tricky subject, as we all know it. You can configure tons of stuff in both sides, and that will highly impact the results. And for actual performance overview, we expect to publish soon a real data about CPU utilization, memory utilization, and in OSD saturation that we are able to get. But just to get a sense of what we have currently implemented for a 3 OSD with 10 cores per OSD, with Crimson, we were able to surpass classical by 40–50%. This is just the beginning. And again, with BlueStore as a backend, which is our main performance bottleneck for now. And I'll explain why in a bit. So the main slide here, I think, is, can I deploy a Crimson cluster today? Yes, with a small asterisk there. Of course, if you're brave enough, if you don't run it in production, we're still missing some basic client support, some basic features, and of course, some failures might occur, as it's still a tech preview, and we are still trying to learn what we support, where do we fail. But we highly encourage anyone who is curious enough to let us know how was the deployment, how it went through, if it actually works. Perhaps we're just speaking here. And to make use, you don't accidentally deploy a Crimson cluster. We have this highly verbose experimental usage flags. You can see here it's enable experimental unrecoverable data corrupting feature Crimson. We made sure no one does it by mistake because we care about your data. So we want you to really know what you're doing. We also have OSD flag and, of course, a monitor pulls OSD flag. Without those flags, the OSD won't boot, PG won't initiate, and you will have just a cluster without OSDs. So you need to remember that. Of course, it's in the documentation. Yeah, so what is ready? Today, we support RBD on replicated pools with basic OSD features such as scrub and snapshots implemented. We had a lot of work being done on recovery and backfill. It also should be there. So a basic workload of RBD on replicated pools should be supported entirely. For future work, we have a lot to go, as the asterisk said there. We have erasure coding. We want to also have erasure coding as pool support. Auto-scaling of placement group, an important OSD feature. Some of the work is splits, a crucial implementation feature of auto-scaling. RGW, we can say quite confidently that the support is mostly there because we know how to support the Rados API. So any clients for now, even a file, should be almost there. But we want to really make sure that we didn't miss any nuances. Of course, QoS, the mClock scheduler that we know, and background scrub scheduling. Today, we just have it by demand. So a lot of things to do. To show it in just in a timeline. Oh, the dot is moved a bit, but that's OK. We see that for if we had RBD with replication. We spent a lot of effort on automated test suite and actual integration suite, not just development cluster, to identify any regressions. We also had snapshots implemented back in Reef. And for Squid, this is our official tech review. So let's give an applause for the Crimson project. Yeah. Still an early stage, as you've seen, and we're still not as confident as, OK, run it in production. But we are there. We want to have users start to try it out. We worked a lot on stability to actually make it work, and recovery and backfill, all the scenarios and workloads, and scrub. For the T release, the next release we have, we plan to replace the backend, and I'll go over all the backend explanation now, to be SeaStore by default. SeaStore is the implementation that will replace BlueStore in Crimson. It's Crimson native in its architecture, so we have high hopes for it to actually show the full image of the results. And some OSD features, and of course, a performance effort. That's why we're here. We want to prove it out. So part 2, don't worry if you're tired. It's not going to be as long as the OSD layer, but I feel it's quite important to show the second part of the Crimson project. So we talked about the next generation of the classical OSD. But if we really want to make use of the modern storage devices we have today, we also need to make sure that our backend implementation, the object store, is also as efficient for making use of ZNS, for example, and SeaStore is how we are going to do that. Today we have BlueStore. BlueStore is the default classic object store. It's suited, as I said, for the classical architecture. It's written with the multi-threaded model. So we had to come up with a compatibility layer. You can see it in the graph here. For Crimson to actually make use of it, we do it using alienized threads. Alienized are meaning they're alienized to the Seastar framework. This is not, of course, best for performance, because at the end, we're still using the same architecture at the end of our I/O path. And of course, we all know that in terms of BlueStore, that we have some CPU-heavy behaviors coming from RocksDB dependence, such as compaction behavior and so forth. And lastly, I would note, BlueStore is still being improved and still being highly worked on by Adam, who I think is here, and he has a great talk tomorrow about the ways that BlueStore is still being improved. But for us, in Crimson, we need to get rid of this compatibility layer and have a full Crimson architecture native support. So SeaStore is how we are going to do that. We build it upon the Seastar framework, same as the Crimson OSD. It's designed to scale better than BlueStore with Crimson OSD, and this is how we should support the emerging storage technologies we have. The metadata will be stored with Bitrees, unlike RocksDB in BlueStore. So this shows the actual change between the two, and some of the letters skipped their box, but that's OK. We can see that we moved from BlueStore in this release. We'll switch to SeaStore while the OSD is on top, and SeaStore will be acting as our backend. Why we used BlueStore as a beginning? BlueStore is highly stable. We all know it, and it could help us to keep developing only the OSD layer without actually caring, in a way, about the backend. And implementing both the backend layer and the OSD layer in the same go from scratch is quite tricky. So we have separated it to two separated efforts. And now that SeaStore is quite stable and it passes CI all of our test suite, we are quite confident it's ready to replace the BlueStore. We'll still keep two tests between the two. But for T-release, this is our plans. Where we stand with SeaStore. For SeaStore architecture, I first note that the tech lead of SeaStore is Inkshin from Intel. He could not join us today. But the main point for Squid is that it's stable, it works, it's fully supported Rados API, all the basic functionalities are there, feature, object cloning, as it said here. We implemented some more feature that will help us to understand how it works, like initial profiling, and some critical features. And of course, scaling and performance optimization. We started with a single core implementation that will just to see how it works, and now we continue to scale and grow, and this is still an ongoing effort we have. If you're curious about backend and object store architecture and you want to learn more, so make sure you catch, I'll link it in the end of the presentation. We have a talk going in depth by Ingxin called Profiling SeaStore, Understanding SeaStore Through Profiling, which I highly recommend if you're interested. For future work, same as we have, the main effort here now that it's stable is performance and profiling optimization, and some more features like such as device tiering, single-layer cell support, and hard disk for tiering, and so forth. For the active contributors, we have a lot of contributors, mostly from IBM and Intel, as mentioned, but we also have a lot of outside contributors and from other companies. So if you are also want to join this list and help us even by deploying or not only developing, feel free to join us. You can scan this QR for our official site over ceph-osd. We have there all the information I sent here, more blogs, links to the tracker, meetings, Slack channel, and yeah, and I guess that's it. Thank you for listening to us today, and we're here if you have any questions. Yeah, go ahead. The idea is to keep scaling. That's why we want to. We don't want to block it. We started, of course, with testing 8, 16, 32, and seeing that we actually see it fully work. But if you're deploying it, I don't want you to stop. I want you to fully exploit what you have available as resource to really saturate your NVMe devices. So yeah, about supported configurables and environments, we still need to do work about that. That's why we have the performance evaluation I noted earlier. We still need to learn how it actually acts in more complex environments with multi-hosts and so forth. But the answer for you is no. Go as far as you want. I saw you first.
What's the ideal CPU? Is it fewer cores with better frequency or more cores and lower frequency?
That's a good question. Right now, we tested more modern devices that offer like more cores. That's the trend that we see right now, and we really want to make usage out of it. For faster core frequency, on the other hand, we have less. I would personally expect it to work less good than with the more cores we have because of this separation that we have, the shard nothing design. But I might be wrong here, and we might learn some new stuff as we try to deploy it on different environments. We are only so limited and want to develop as quick as we can. So that's a good question. Thank you. Patrick. That's actually a good point that I was stumbled upon, like I think a week or two when we started the evaluation for 8.0. Because we map each core into its each PG into its core, we may not expect the recommendation of number of PGs, same as we have in Classic, to be relatively to the pool size and so forth, and we will actually need to make it like, let's say, recommend like 128 per OSD always, just to have like a good separation. So I think it would be quite different than Classic, but still no hard recommendation. Right now, the more the merrier. Again? We try to use as much common logic and data structure we have in the OSD. We have the famous OSD types header file. we don't want to rewrite it. We already have a good working ceph-osd architecture. We want to use all the types, all the data, but the logic and the actual execution would be different. So the data type should remain the famous one that we are familiar with already. Yeah, you go and then you.
Okay. So is it true that each PG will have its own port number listing? Because otherwise you have traffic coming into the port of the OSD and then switching to different core. I heard rumors that might be a change going on there.
With Crimson, specifically? We did realize also, most recently, as you can see, we are on the go here on the fly, that you should keep your reactor threads number on cores on the same NUMA socket on your core to not actually share like data between sockets to keep it more efficient. And for the most recent evaluation, we actually use that kind of deployment. And I think we would officially also recommend that. But we've seen some behaviors around memory usage that we didn't expect. So yes, I would expect you to have each OSD reactor threads in the same socket. But we may have some artificial symptoms that we still need to learn why they're there.
Yeah, I was thinking about SeaStore when it comes to storing data. There are different kind of methodology that you need to think about depending on what kind of device you have in the background.
Right.
So this is just more efficient, so it doesn't really matter if you are using hard drives with SeaStore.
Right. The fact that we get a chance to rewrite our backend implementation from scratch, supporting ZNS, for example, would have been really challenging with BlueStore, almost impossible. And now we have a chance to have dedicated architecture for each storage type device you have. We plan to also support, of course, hard disks for, let's say, storing cold data and so forth. So yeah, we want to be as good as we can. But yeah, thank you. We're using B-trees to model to host our metadata, where we use DroxDB in BlueStore and cause some heavy behaviors, CPU behaviors and dependence. So we had like tricks to go above them, and that's what we want to avoid. So we have our own implementation now to store the metadata with B-trees. Again, seems like you're into SeaStore architecture. Make sure you scan the QR and see the talk I've mentioned earlier, where we really go in depth and not just few points and like high-level designs. Patrick, I saw your hand earlier. Is it all good?
Why object-only in array decoding support for Tentacle?
Again?
In your Tentacle, Charlie said array decoding object-only.
I don't know. Might be a mistake or a legacy that it's bitten in the wrong. I don't see a reason why it should be object-only. Maybe because we plan to support for a beginning RGW and not file system for a start, and that's why it said like EC for object-only and not for other workloads. But I see no reason for it to work differently.
Perhaps it's because ceph-osd uses X-adders and then
It will use what?
ceph-osd uses X-adders and PC.
Yeah, I recall now that we may have saw some issues about implementing that for FS as well, because it has attributes, right? And like that, it's not as trivial as for objects. So we start with object, see it works, and move on. Thanks, Patrick. I guess that's it. Thank you very much.
Thank you.